Hello, good afternoon. Okay, so if you can hear me, just give some feedback over the chat. Okay. Okay. So good afternoon, everyone. So welcome back to the course Finite Elements KM32003. Okay. Today we will move into another sections or topics related to the plane stress and plane strains problem. Okay. So today also we will introduce these two type of analysis problem using a new type of elements. Okay, we call it as a constant strain triangular elements. Okay, so the topics of today's will address the following course outcome. Okay, again we will apply the mathematics, science and engineering to model it. Okay, then after that we will try to identify and approximate the boundary conditions, okay, for our discrete model before we solve them, okay, for in mainly on the structural problem, right? So just a recap on the previous slides, okay, that I have shown to you long time back. Okay, I think in the second lectures. Okay, so as we know, okay, for any finite element models, okay, we can always have our three-dimensional models as such. Okay, and from that we can always simplify or convert our physical problem, assuming this is the physical three-dimensional problem that we going to solve. Okay, but we can always convert them into different kind of finite element model. For example, very simple line types, or maybe you can call it as a beam. Okay, so you can assume this is one beam. Okay, another beam, all right, or maybe a string or whatever it is. Okay, then on top of that, now we move into what we call a shell problem. Okay, a two-dimensional elements problem, right? Instead of using a single or one-dimensional elements like a beam, okay, we can also convert or use what we call as a shell elements or two-dimensional elements. For example, here we use maybe uh, rectangular types of elements, okay, to represent the model, right? So today our focus would be on this two-dimensional problem. Okay, and because of that we have to define what is the plane problem. Okay, that divide into two generally. Okay, we call that as a plane stress analysis problem and the plane strain analysis problem, right? So as you can see, in this chapter we will consider basically two types of element. The first one is the constant strain triangle, CST in short. Okay, and another type would be the four nodes rectangular elements, Q4. Okay, or quadrilaterals with four nodes element, right? So today our focus will be on the CST. Okay, then we will continue with the Q4. Okay, elements in the next lecture, right? So these two uh, element itself, basically we can call them as a shell or two-dimensional elements. Okay, so in the Lisa FEA software itself, okay, you can see that there are tri 3, okay, which is basically the CST. Okay, or tri 6, which have the 6 knot. Okay, this means there is a mid knot, yeah, with a mid knot element, right? Then there is a quad 4, okay, which is the Q4. Okay, and they are used for a shell types of a problem, right? So here when we talk about a shell or two-dimensional elements problem, we are actually referring to a problem that occurs on a plane, okay, which involve x and y axis. Okay, so if we intend to use a planar type or two-dimensional elements itself, okay, then this element should have three or more elements. Okay, for example, for this constant strain triangular elements, CS3, there are 3 nodes. Okay, for the Q4 there are 4 nodes, and so on, right? As you can see from the Lisa menu itself, they shows that for a static two-dimensional elements, you can actually use a different type of shell elements, okay, like tri 3, tri 6, quad 4, quad 8, quad 9. Also, you can try to use beam and so on, okay. But then the only difference between what we learn for beam, okay, beam type of element, the one-dimensional elements, and the two-dimensional elements is that there is a considerations of the area, okay, within the element itself, okay. Whereas in these cases, okay, we just represent it with a single line, okay. Right. So the calculations or the methods of the finite element method still remain the same. You still have the so-called 7 steps of finite element methods, okay, to apply this, right? So here is the examples of a problem extract from the textbook written by Professor Logans, okay, which consists of a simple beam problem, okay, which previously in our previous methods, okay, we may assume this as one single particular beam problem, right? Either with two elements, okay, element 1, element 2, or you can break into more elements, right? Okay, so we can represent that as a single so-called beam, okay, a single one-dimensional beam, okay. But now we will try to expand, okay, where we also consider the shapes, okay, along this vertical directions, right, for examples, okay. So therefore you can see that this is a rectangular or a Q4 type of elements, okay, whereas this is a very obvious triangle elements, okay, the CST type of elements, all right. So you can see that we can always approximate, okay, depending on the type of element that you select to model your physical problem, right? So these elements, again, as previously or it is required by the finite elements algorithms or methods itself, okay, all these elements must be connected with a common node, right? So if you want to connect more than one elements, okay, then these elements with the same node must be a common node, okay, shared by all the elements, okay, around this, all right. So make sure they are shared together, and also they share a common edges, okay. So if you look at this figure itself, okay, so these edges itself, they are shared, okay, with the same nodes, okay, M, I, and N, okay, same nodes, okay, shared by this element 2, 3, and 4, these 4 elements, right? Okay, whereas the edges also, they are shared, right? So the sharing of edges and nodes are very important to ensure that the structure are continuous, okay. They will not form like later on when they deform, this side have one edges, okay, the other side have another edges where there is a void, okay. In real cases, there's no void in between them, right? So we would want to make sure then they share it, okay, so that they displace or they transform, okay, with the same degree of values or degree, right? Okay, so this concept is very important to ensure that the derivations are actually proper, okay, to make sure they can be solved properly, right? So again, very important is that when you have this particular problem, okay, whenever you use FEA software itself, they actually have a functions called merging of nodes, okay. So sometimes when you create a model, right, so you may have 2 different model, right? So sometimes the model will have like maybe 0.01 millimeter, right, difference. But then when they create the models, they may have different nodes, all right? So maybe there is one small node, okay, this node belong to this, right, and this node belong to this so-called part or element, right? But then you can see that these two particular nodes are very close, and in fact you may want them to be combined together and move together as a single node, right? So therefore in this case you have to detect a very near nodes, okay, and merge them together into a single node so that they share a same form of so-called nodes, right? So these are those kind of considerations or discretizations problem or meshing problem, okay, when you deal with a three-dimensional, or maybe when you deal with the finite element analysis, okay? So besides selections of the elements, the meshings and the merging of all the relevant nodes, okay, to make sure they are commons are very important for you to actually solve, okay, for the software to solve it, or else you may either get a very strange result, or you may have the software may show you some type of error like a discontinuity error and so on, okay, which they may not able to solve later on, okay? So here first we will introduce you with the plane stress concept or plane stress analysis, okay? So in this plane stress cases, okay, it is actually defined as a state where the normal stress and the shear stress directly perpendicular to the plane, okay? So you can see that this is the plane of the structure itself, okay? When the normal stress and the shear stress are actually perpendicular to this plane, okay, then and they are assumed as zero, okay? So therefore what it means is that for example, for this particular cases, okay, what happens is that this structure there is a thickness, okay, and the forces is actually acting like across perpendicular to this parallel to this plane itself, okay? Therefore whatever what we should say, but whatever forces that maybe there is a hole or whatever it is, okay, in between it, okay, therefore in these cases you may want to consider only a plane, okay, which is sufficient to solve for the stress, okay? So you can see that the load is acting over here, right? The load is acting over here, okay, and over the z directions actually there are no forces acting, okay? Therefore we say the normal stress in the plane, particular plane to this plane again, right, is actually zero. So therefore in these cases we just consider this 2D plane is sufficient, all right? So what make this the needs of solving, like you may be using a triangular the CST elements itself, is that sometimes you may have a problem that includes hole, right? So for example here there is a hole in between, or maybe there is a fillet, okay, reductions of size where there is a stress concentration over this area, right? So you may want to represent them with Q4 or maybe CST, all right, to approximate the shape of it, okay? Then this would somehow make use of, or maybe you may not able to represent it with a simple beam now, right? So as we say previously, you may easily represent the problem with a single beam element and so on. But then if there is a hole in between and other type of so-called stress concentrations, therefore the beam element may not be useful now, okay? And that's why you have to now move on to the higher degree of freedom, the shell type of problem, okay? When we apply the shell type of problem, again we have to make sure that the forces only acting along the plane, all right, only along the plane, not the other side. Therefore, in this case, we can say the plane stress analysis problem, all right, so where the force is actually acting perpendicular to the plane itself, okay, along the surface of the plane, right. Whereas for the plane stress problem, okay, plane strain problem. Plane strain problem will define that the state of strain, okay, in which the normal strain in the xy. Now the xy axis is so-called at the cross sections, okay, cross sections of your structures. Alright, so in these cases, okay, this maybe look like a triangle, okay, so this is maybe another triangle, right. So you can see that actually along this so-called cross-sectional area, okay, the state of strain, okay, normal to this xy plane, okay, where there is a changes and so on, actually can be considered as 0, right. So along these directions, they are so-called, the changes are very minute, okay, that's they are 0, right. So therefore in that case, okay, it will be suitable just to analyze only one particular cross-sectional area as a two-dimensional cases. We call this as a plane strain analysis, okay. So for example, now we can use it to analyze a very long underground box covered, okay, maybe a rectangular box, okay, which may be spanning with a length of maybe 1 kilometer, right. So if we want to analyze it, okay, we know that the forces is constantly along the long structures, all right. Therefore we can simplify our problem by analyzing only the two-dimensional cases, or we call it as a shell problem now, right. Okay, so in this case we can extract and only analyze for the cross-sectional area, right. So the assumptions for the plane strains are, again, we need to say that they may be very long, okay, a long body, okay, with a constant cross-sectional area, okay, constant cross-sectional area, and also the load acting along it should not vary, okay, they should be the same, so that every cross-sectional area will be subjected to the same type of load, okay. So in that cases, if you would want to analyze this, okay, then we may want to apply what we call only a unit thickness, okay, since the thickness now is the length, right, okay, instead of the proper thickness itself, okay. Then in this case, you just use a unit of thickness, maybe 1 meter or 1 mm, okay, to represent that particular thickness, okay. Whereas for the previous case, plane stress analysis, okay, we will assume that the thickness may be very thin, okay, a thin thickness, okay, so that whatever changes in the thickness itself is very is negligible actually, right. So these are the two cases that you may have to consider, okay, when we are considering for two-dimensional elements, right. So if let's say now you have a problem where the load varies, okay, then in that case you may not able to use the two-dimensional. In that case, you may need to extend it to a three-dimensional cases, okay. This is where we will start with the very simple elements, okay, the first one-dimensional elements. We check whether it is sufficiently to represent the whole problem or not, okay. If there is a stress concentration, then we may want to move into two-dimensional problem, okay. When the problem now become more complicated with changing shapes throughout the three-dimensional or xy directions, then in that case, then we may want to further increase the degree, okay, to a three-dimensional problem, right. So now we will come back to the two-dimensional problem, or the 2D analysis problem, okay. We will start to define the two-dimensional state of stress and strain, right? So I believe this is a very familiar figures for you in the engineering materials, or maybe the strength of materials. Okay, basically these are the basic of the material, okay, where we consider the stress, okay, occurs, okay, in the in the elements or in the material itself. Okay, so yes, you just imagine this small rectangular is actually come from maybe a very big shapes. Okay, it come from very small rectangle, okay, of it, right? So in the rectangle itself, okay, each of these small rectangle, actually they are subjected to stress in xy direction as well as the shear, okay, and the shear basically should be the same, so that the moment of equilibriums are so-called maintained, okay, in one part. Okay, so the moment of equilibrium should be equals, okay, in the xy, right? So they must be in the equal values itself, okay, whereas in the x and y there is a shear stress acting, okay, there is a normal stress acting, okay, the sigma x and sigma y acting in the x and y directions, okay, on the elements of the length dx and dy, a very small length of dx and dy, okay. So based on that, we would see that there are actually three independent stress axes, okay, basically the stress, okay, in x and y direction as well as the shear, okay. So we can combine them into a so-called vectors, okay, which consists of the three independent parameters. All right, so these three independent parameters that we intend to solve later on, okay, which we usually, for a structural problem, we would intend to know what is the actual stress and as well as the shear, the shear acting on that particular part, right? So this is where we would want to solve using the finite elements, okay, maybe for a very complex shapes, okay, and we would slowly form in this shape, I would say. All right, so first thing, you just have to recall or remember that there are three independent stress to be solved for a two-dimensional problem. Okay, so now once you have these three independent stresses, okay, to be solved, okay, we would now want to indicate the normal or the nodal displacement, okay, based on our elements itself. All right, so once the nodal displacement are known, basically we can relate the displacement with the stress, okay, in order to solve these three parameters, right? So we still need to know the displacement. Okay, now on top of that, okay, from the two-dimensional state of stress itself, okay, basically from this stress, okay, there is a positions, okay, we will say a positions, okay, or a principal angle, at the principal angles where the principal stress would be the highest, okay, and the other side, the principal stress will be minimum. Right, so at this principal angle, the shear would be equals to 0. Okay, so this is again the basic definitions of what we call maximal principal stress and minimal principal stress. Okay, this is just a highlight of the stress term that you have learned previously, right? So there is a maximum principal stress, minimum principal stress that are being defined for a two-dimensional problem or elements, okay, with just a different node itself, right? So this is the maximum and minimum normal stress or principles. When the shear is 0, we call that as principal stress. For cases when it is not 0, then we may just call it maximum and minimum normal stress. All right, so that is the definitions, and you can also refer to this diagram. Okay, you may see this as a Moore diagram, okay, the Moore circle, all right, where how the stresses, okay, actually change according to the principal angles, okay, or the rotations of the elements itself, right? So now moving forward, right, so that is just a brief idea of what type of terms that you may encounter soon, all right? So on top, moving forward from that, okay, it shows that the element is now, assume that it is very small. We call it as infinitesimal elements, okay, to represent a two-dimensional problem or state of strain problem, right? So because of the stress and because of the load, okay, the stress as well as the shear itself, the elements may translate, move, okay, as well as deform, okay, in this so-called deformations, right? So we can express the strain, okay, the changes as such, okay. So this is the strain in x directions, the strain in y directions, as well as the shear, okay. The shear related to this, okay. So these three equations would be used, okay. The theory behind these three equations, okay, will be used to derive for the relationship between the stress and strain later on, okay. You can see that this is the strain, right, and this is this so-called, we can say some kind of displacement, right? So there is a displacement du, okay, changes, okay, respect to the original length, okay. We have du, and there is a another, there is a dx, okay, the original length, and there is a du, the changes along the x directions, okay, that define our strain, right? Okay, so meaning to say, if we would able to solve for the nodal displacement, we would able to get the strain, okay, and based on the strain, we can relate back to the stress of the elements later on, right? So here we call the strain, okay, as the normal strain, okay, normal strain, whereas the other one, okay, this one we call that as the shear strain, okay, shear strains, okay, that cause the elements to change shapes, right, instead of elongate, all right. Okay, so back to the strain again, okay. So this strain, now you will see that they can generally again express in this form, okay. Again, three independent parameters, okay. Now you can recall that in the stress, okay, previously in the stress there is three independent stresses, okay, and eventually for the strain there are also three independent parameters. So you can form a relationship to connect them together, okay. We call this as a stress-strain relationship, okay, with a constitutive matrix, okay, D, right, to represent the relation between them, right. So in the previous one-dimensional, we will say this as the Young modulus and so on, right? But then because of the strain and the shear being involved, we just combine them and call this as a stress-strain matrix or constitutive matrix, okay, that relate the stress and strain relationship, right? So in this particular relationship also, okay, we make an assumption that the material itself is an isotropic material, okay, meaning to say the directions, okay, the directions of the material itself, okay, I will say the material property of the material itself will not change according to directions, okay. In the x direction, y direction, and the z directions would be the same in terms of the Young modulus, maybe the Poisson ratios and other things, okay. We call that as isotropic materials, all right. So the only difference when we apply for this constitutive matrix itself, is depending on the type of problem, okay, that we're going to define. All right, either it is a plane stress problem or a plane strain problem. Okay, for a plane stress problem, we will assume that the stress shear along the z directions would be 0, and because of that the constitutive matrix would be in this form. Okay, so therefore we just have to define the type of problem, we apply the proper of the matrix, okay, to our relationship, right? Whereas for a plane strain problem, we will assume that the strain, okay, previously the stress, okay, is 0. Now the strain along the z direction is 0 because it's long enough, okay, it will not do any changes along the z directions, right? Therefore the strain is 0. Okay, so based on these assumptions, okay, then the constitutive matrix would be given as such, right? So based on this constitutive matrix itself, you can see that the material property that you need to tell the software or the finite element software would be again the Young modulus. Okay, but then another new terms that you may need to provide is the Poisson ratio. Okay, how it would change, okay, when one side in the x, let's say in the x direction change, okay, how it will affect the y directions. Okay, there is a Poisson ratios relationship between them, right? So make sure you understand what type of problem first before you select the equations, okay, to be solved, right? Then for the derivation itself, again we apply the 7th step. Okay, this is just an illustrations for the derivation for the CST elements. Okay, we would form the stiffness matrix. Okay, and then from the stiffness matrix we would combine them using direct stiffness methods, okay, to form the assemblage total stiffness and solve them accordingly, right? So the idea is still remain the same. Okay, we have to define the CST, right? Yeah, maybe if you have questions, you just put it in so that we can address it from time to time, right? Before I forget, right? So yeah, from here as we continue from here, all right, so to illustrate the steps is that again we have this problem. All right, so this is a thin plate problem in tension. Okay, so in tension since this is pooling, okay, so we can always mesh them, like break them into two parts. Okay, then maybe we can form like this. Okay, so we have one triangle, two triangle, three triangle, four triangle. So we may represent this as element 1, 2, 3, 4, right? So if we want to just to do a practice, you can start with this, right? Then when you are familiar or when you can program it, then you can move into a more complex. Okay, you can break them into 1, 2, 3, 4, 5, 6, 7, 8. Okay, total 16 elements. Okay, and if you use the software, you can even mesh it into maybe hundreds. Okay, depending on the accuracy that you intend to get later on, right? So here you can see that this problem, first the tension is on the surface, okay, across the surface. Therefore in this problem you may just consider what we call as a plane stress problem, right? Okay, so we just assume this is a plane stress problem, and once we mesh it or we discretize our problem into elements. Okay, so you can see these elements may consist of three nodes. Okay, I, J, and M. Okay, I, J, and M, right? So you may have I, J, and M, okay, on the space. Okay, on the space itself. Okay, I, J, M, and each node itself we can define as with a coordinate x, I, y, I. Okay, and each of these may translate. Okay, will move in form of displacement, okay, given by ui and vi, okay, for the node I. Okay, so there are two two things here. Okay, xy represent the coordinate, and the u and v represent the displacement in the x and y directions, right, for that particular nodes. Okay, so now based on that, okay, now we will know that every single node itself has 2 degrees of freedom, okay, the u and v, okay, in both directions, displacement in the x direction and y directions. Okay, and also you can see that why we would like to use CST itself is that it can be easily approximate an irregular shaped body. Alright, for example, if you have a plane, okay, with a circle, right, so therefore again, as I say, you can always easily mesh it, okay, with triangle, okay, to approximate this particular circle itself. Alright, so this is where the meshing will comes in, alright, to approximate this particular circle. Right, then another advantages of this CST would be it is relatively simple, okay, comparatively simple, because it's only involved three nodes, okay, 3 nodes, meaning to say the number of unknown to be solved will be reduced, okay, the number of equation involved will also reduce in terms of the expressions that you will see later on in the displacement functions, right? So you can always mesh into either very coarse mesh or very fine mesh later on, right? So since every single displacement, okay, for the node itself, we can break into 2, u and v. So basically you can have 6 nodal displacement to be solved. Alright, so you just represent this into the 6 by 1 matrix. Alright, so moving from there, okay, now in order to express the linear displacement, now previously in the beam elements we only consider either x or y, right? Okay, but then now it involves both directions, okay, the u and v, therefore and this u and v also depends on the x and y coordinate. Therefore, for the u displacement functions, okay, the simplest one would be involving three unknown, okay, where you have x and y, okay, with a constant, okay, so you can express as a1 a2x plus a3y, right? Whereas for the v, another displacement in the y directions, okay, that depending on the coordinate of x and y, again we would express as it as a a4 plus a5x plus a6y, right? So based on these 2 displacement functions, linear displacement functions, now we can slowly move on with that, right? So first thing, these displacement functions must ensure the compatibilities issues, okay, they must be sharing, okay, the nodes and the edges must be shared between the elements, so that whenever this element change, okay, it will be reflect on the other side as well, okay, and also the other side would affect the other side, okay, so eventually you can have a common nodes and edges that will move together depending on the effect by all the elements adjacent to it, okay, next to it, right? So now based on these 2 displacement functions, right, we can further expand, okay, since we have a1 to a6, okay, we just break them into a1 and to a6, okay, using this matrix form, okay, and we represent in general as a phi, okay, the general displacement function in this form, okay. So this form actually, when we resubstitute, okay, the coordinate of the nodal points, okay, we have xi, yi, okay, xj, yj, okay, and so on, right, for every single node, because this CST has 3 nodes, okay? There is I, J, and M nodes, right? So U itself, there is already 3 equations. For the V, another 3 equations, right? And they are related to the, again, you can see A1, A2, A3, same A1, A2, and A3, okay? To ensure that they are consistent, they are what we call compatible, right? Compatible between them, okay? Okay, so you have U1, UI, UJ, and UM, okay, expressed in this particular form, okay, based on these equations, okay. For this, the other equation, the other 3 equations, you can again form another equations, okay, another equation in the similar form, right? So in order to solve for A, okay, later on we always want to solve for the unknown, okay, A1, A2, A3, A4, A5, A6, right? So now we just concentrate on the A1, A2, A3 first, because the formulations or the methods to solve for A4 to A6 is the same, right? So for the A1 to A3, okay, we form these equations, and since they are in matrix, we can easily solve them simultaneously, okay, by applying an inverse matrix, okay. So this matrix, when we take inverse of it, okay, meaning to say we move to the other side, then when we solve this particular part, we would know the A1, A2, and A3, right? So by doing that, we can get A1, A2, A3. Same thing for the A4, A5, and A6, okay, with a simplifications of 1 over 2a, okay. This is because of the inverse matrix, okay. We have 1 over 2a, where this 2a is actually the determinant, okay, determinant of the matrix itself, okay, determinant of this matrix itself, okay. So determinant is the a x j y m multiplied by x m y j, okay, and so on, right? Okay, and the a also coincidentally, this represent the area of the triangle itself, right? So once we obtain that particular form, okay, we can easily now resubstitute it into the matrix, right? So previously in this particular form, right, in this particular form, we already have this A1, A2, A3, right, relationships, okay, which, okay, tells us what is the displacement, right? So once we know the A1 to A3, okay, we can substitute back into it, okay, to form our displacement function, which is yeah, it looks like very complex, okay, but when you can program it, basically it's just a number of plus and minus, right, and multiplications, right? So it's very straightforward ideas, right? So you can always expand it for V as well, okay, which involve the A4, A5, and A6, okay. U involve the A1 to A3, okay. The V involve the A4, A5, and A6, right? So you get these 2 displacement functions, okay, complete displacement functions, okay. So from the displacement functions, again, if you would want to express them in the form of shape functions, okay, then you just break them into, yeah, just identify the common terms, okay, then you can form the shape functions, right, that represent the contributions of the displacement on the particular, in this case is the surface, okay, on the surface, okay, by the three axes, okay, the I maybe, or 3 nodes, okay, by the I, J, and M node itself, right? So again, the shape functions rules, okay, the summations of all the shape functions over the surface, okay, over the same elements must be equals to 1, okay, to make sure that when they combine them together, they still integrate, right? So the summations of the displacements should be proper, right, in the end, okay. So once you get the shape functions, okay, then you can re-express, just rearrange the order of the matrix, okay. So eventually you come to this particular form, okay, or in short, all right, this is the shape functions matrix, and this is the displacement functions, okay, or displacement matrix, okay, sorry, displacement matrix, okay, or the nodal displacement, right? So remember, this is the shape functions, all right. Okay, so far no questions yet. All right, so next would be now further onwards, okay, we should also consider to ensure that the completeness of the shell element or the CST element that are being used. Okay, the first thing that we have to ensure is that the element must be able to translate uniformly in either x or y directions without or to rotate without straining. Straining means change in terms of shapes, okay, to deform, right? They just translate without deforming, okay. So what occurs is that based on our principle or knowledge, okay, a shape, okay, they will maintain their form, okay. Let's say you have this form, right? So this is a form, okay. If we apply a force, okay, not on that particular segment, okay, whatever we do, it will only move together, right? So they will only translate unless in this particular part we put some force on it, okay, then only this particular part will deform, right? The rest will only translate, right? They will just move to translate, but then this particular part deform, right? So based on that idea, right, therefore you can see that if the load is only acting on this particular segment, okay, therefore only this particular segments, okay, only these particular segments the element may deform, okay, meaning to say this, you can see that this one is longer than the bottom, right? Whereas originally they have the same length, okay, but then because of this particular part, okay, they undergoing a straining, okay. Whereas on the part where there is no load acting, okay, it should allows the equations or the CST elements displacement function should allows it to just just displace without deforming, okay. So you can see that the length of these two sides is equals, okay. They only rotate and displace, okay, without deforming, right? So this ensure that the whole structures actually we call it as complete, right? So that it will not force all the elements to change shape, okay, or to remain there, okay. It must be able to translate, okay, in order to maintain the real situations of it, okay, of the problem, okay. So once we obtain that part, okay, next would be we would want to define the stress-strain relationship, right? So stress-strain relationship, we just apply back the equations that we have mentioned previously, okay. General equations for the strain and the stress, okay, that's relate with the type of problem that we would want to solve, right? So let's take this part again, right? So you can see that there is for a CST, okay, so the strain X is equals to A2, strain Y is equals to A6, and the shear strain is equals to the A3 plus A5, okay, when we solve it simultaneously to solve for this, right? So based on this, okay, you can have a relation between the stress and the strain itself, okay. Again, if we want, okay, we can always differentiate, okay, partially with respect to the direction x or maybe y, okay. So in this form we just simplify the partial derivations, okay, with respect to x by using the notation of comma x, okay. So when you see a comma x, meaning to say it is differentiate respect to x, okay, if you see comma y means respect to y, right? Whereas the front part represent the not number, not numbering. Okay, so you may want, you may express the so-called displacement in the shape functions equations. Okay, after you differentiate respect to the x or maybe y to obtain the strain. Okay, you would come to this particular form, right? So at some part of it, okay, they may equals to 0. Okay, some part of it, okay, since they are constant, they may become 0, right? So if you differentiate respect to for the shape functions again, because the shape function is given in this, right? Okay, based on our previous derivations. Okay, then again when we apply to this, okay, the shape functions have to be differentiate respect to x. Okay, so we have to differentiate respect to x. Okay, so let's take these examples. Okay, the ni, okay, if we differentiate respect to x, meaning to say we have to identify whether there is x or not in this. Okay, so since it's only alpha I, no x involved, so these terms become 0, okay, when we differentiate respect to x. Okay, then for these terms, since there is an x there, okay, when we differentiate respect to x, this become beta only. Okay, and this part, okay, no x involved, so becomes 0 again, right? So eventually when we differentiate these shape functions I respect to x, we would get beta I divided by 2a, okay, similar to the others. Okay, so we will get this. All right, so from there we just combine them back into our equations, our previous relationships over here. Okay, so you will get basically this is the strain in x. Okay, this is the strain in y, this is the shear strain, right? Okay, to in this equations. Okay, so based on that particular equations, okay, we can again group them together in the matrix form. Okay, group them together in the matrix form, and this is the displacement. Okay, this is the displacement, and this is what we call it as the gradient matrix. Okay, this is the gradient matrix, right? So you can see that the strain is now related to the gradient matrix multiplied by the displacement matrix, right? So now back to the stress-strain relationship. We know that there is a constitutive matrix involved, right? And this strain and the stress is given as such. Okay, and this strain matrix is related to the gradient matrix multiplied by displacement. Okay, we can replace that with this. Okay, therefore we can solve for the stress, okay, acting on that particular element itself. Okay, on the particular CST in this case. All right, so the D remain depending on the type of analysis that you are going to apply. Okay, so once we get that one, okay, we have the relationship between the stress and strain. Okay, and this strain itself, the stress itself occurs at the centroid of the center of the element itself. Okay, since this is sigma x, sigma y, and shear stress xy, right? So if you have a CST like this, okay, so the stress will be represented by the centroid of it, right? Centroid of the element itself. Okay, so now in order to derive for the stiffness matrix, okay, we would now use what we call a minimum potential energy principles, okay, to derive it, right? But then in this case, since this is a bit complex, okay, and I would not expect you to actually express just an idea of it, that in order to derive it, it is based on the principle of minimum potential energy, okay, where the total potential energy is equals to the strain energy, okay, minus all the losses of the energy due to the body forces, okay, you can see the minus here, okay, minus, okay, or maybe due to the concentrated load, and also the surface tractions, okay, involved onto the element itself, okay. So based on that equations, we just plug them in, okay, into this, okay, to get the total potential energy, okay. Take derivative with respect to the nodal displacement, okay, then apply the thickness, okay. Remember, when we deal with the shell problem, for the plane stress problem, we take the thickness, okay. For the plane strain problem, we take the unit thickness, right, of the problem itself, okay. So we take for an element with a constant thickness, okay, so we have to so-called multiply with the thickness, okay, and also throughout the multiply with the thickness of the elements itself, right. So again, eventually we may get into this particular form where this is the gradient, this is the displacement, okay, gradient, the thickness, the area, right. So they have some kind of relationship in between them, okay. So group them together. This is the form of each of this is a 2x2 matrix, okay, 2x2 matrix, so you will get 6x6 matrix at the end, okay. That relates the force and the displacement, okay. So this is for us to solve for the displacement itself, okay. We would want to solve for the displacement, because from the displacement only we can get the strain, and from the strain only we can get the stress, right. Okay, so if you see the flow, previously we talked about stress, then stress relate to strain relate to displacement, right. And this displacement actually relates to the load applied to the element, alright. So this is the relationship, the load multiplied by the stiffness matrix, okay, the load is equals to the stiffness matrix multiplied by the displacement, okay. Then from there you will get if we know the forces or the load acting, then we will get the displacement, right. So based on that, okay, we can always combine them or assemble them together into a global stiffness matrix, okay, using the direct stiffness method, okay. And since this involving a two-dimensional plane, okay, where rotations and so on will occur, okay, therefore we would want to relate the local and the global displacement as well, okay, for the displacement, for the force, for the stiffness matrix, okay, which is given by this particular relationships, okay. I believe you may see familiarity between this transformation matrix between the local and the global stiffness, okay, in the previous lessons, okay. So we just apply that to get the displacement, the force or the load, and as well as the stiffness matrix, okay. Based on that, we can always transform, okay, accordingly, right. So once we get that, we will solve them simultaneously to get the nodal displacement. Once we get the nodal displacement, now we will substitute it in to get the nodal strain, okay, to the element strain. From the strain, then we get the stress, all right. So you will come back from the force, okay, back to what we want, okay, or we tend to get later on, right. So far I think no problem so far yet, right. Maybe because mainly on the derivations, okay, but the idea is that it gives you an idea on how things change inside the equations and what is the parameters that are important, right? Remember, there is a Poisson ratios, there is a Young modulus, okay, that being applied, okay, and the assumptions of the thickness, okay, for the plane stress and the plane strain problem analysis, right? So these examples just illustrates one single elements, okay, one single element itself, okay, with, let's say we take this as a plane stress elements problem. Therefore, what we can do is if it is given all the displacement, okay, so if everything is given, right, meaning to say we do not have to solve for the force equals to, okay, because we do not need to get this one because this is given, right? So this example is only for you to use the displacement and to relate it to get the stress, right? So using this, okay, so we have 3 nodes, okay, labeled as node number 1, M is node number 3, I is node number 1, J is node number 2, and the coordinate is given as 0, 1, 0, -1, and 2, 0, right? So coordinate is given, displacement for every single node is given, right? So what we need is just to apply it according to the proper equations, right? The Poisson ratio is given, the thickness is given, the Young modulus is given, okay? So you have sufficient informations to start with the calculations, right? So the solutions would be, you may want to evaluate the K, okay, to obtain the so-called beta and gamma, right? So 2.6.10, okay. So once you get that one, then you may obtain the B, the gradient matrix, okay. Once you get the gradient matrix, now for the plane stress conditions, apply the proper constitutive matrix D, okay, and then you multiply accordingly to obtain the K, right? Then you should able to obtain the stress, okay, as such, okay. Once you get the stress as such, and what you need is you apply the equation is 6.1.2 and 6.1.3 to get the principal stress, okay. You will get the principal stress, okay, as given as this, okay. So you just refer accordingly, okay, and this is the principal angle, okay, where the stress is equals to 0, right? So this is how you may work on it, okay, and these are the steps, okay, that applies into our discussions or the guide here, right? So you may just go through it on your own, right? Because it may take some times for you to understand, right? So I just brief you the guides, okay. From this is what we actually doing, right? So you get all these parameters, okay, get the B, get the D, substitute, solve for the K, right? So once you solve for the K, then perform accordingly to get the stress, okay. Once you get the stress, evaluate using the principal stress equations, okay, with a plus and minus to get it again, and as well as to get the principal strain, principal angle, okay, itself, right? So these are the 3 informations or stress information that you may obtain, okay, from the finite element software, okay. This is how they compute it, all right, using the CST elements, right? So again, for the example number 2, it's very similar, okay. This is a plane stress problem, okay, very straightforward. You can see that force is along this particular plane, right, along this particular plane. Therefore, we just assume plane stress problem, okay, with the thickness, okay. You can always break them according to whatever number of elements that you would like. Okay, so for simplicity you can break them into just two elements, solve them right one by one. Element number one, element number two, element number one, element number two. Okay, combine them together, right? Since they are not 1, 2, 3 and 4, right? So therefore u1, u2, u4 and u3 and so on, right? So do the stiffness matrix, direct stiffness matrix, direct stiffness methods. Okay, combine them according to the knot. Okay, then based on that, apply the proper equations, boundary conditions. Okay, at the support, right? So here we have the support. Okay, the reaction force at the support as well as the boundary conditions given at the end, right? So there is 5,000, okay, acting at the knot 3 and 4, right? So at the knot 3 and 4 there are forces, okay, and that results since at the wall, okay, no displacement allowed, only displacement at the end. Okay, so there is uv, okay, at the knot 3 and 4. Okay, so solve them accordingly. Okay, you should able to get the answer, right, as given, right? So from this problem you would see that there is a small displacement in the y directions. Okay, in the y directions. Okay, whereas for the x directions they are higher. Okay, but then you can see that this is quite high. Okay, not number 4, in the y directions the displacement is quite high. Okay, even though we would assume that forces only acting in these directions, the changes may not be that big actually, right? So if we compare to the analytical solutions for displacement for a beam, okay, for a beam we just quickly calculate at the end of the beam the displacement for a cantilever problem would be given as such. Okay, so basically yeah, more or less there, right? More or less there, but then there is still error depending on the number or the error that you expect. Okay, the type of accuracy you would want to expect on it. Okay, if you want higher accuracy, then you may just write a program, okay, in Excel, whatever. Okay, just break them into more elements. Okay, yeah, depends on, you can use 1, 2, 3, 4, 5, 6 elements, okay, and so on, right? Okay, so based on that, okay, once you get the displacement, put in the proper matrix, okay, the gradient as well as the constitutive matrix. Okay, this is the constitutive matrix for a plane stress problem. Okay, you should get the stress, okay, acting on the element itself. Okay, for element number 1 as well as the element number 2. Okay, you just have to calculate accordingly, right, for each of the elements, right? So from there you should expect, since in this problem only one directions, okay, so you will expect the internal stress, okay, occurs should be similar, okay, for both elements. Okay, but then if you have a circle, okay, or not a stress concentration occurs, then you will see that the stress, okay, at different positions of the element may change accordingly, right? And that stress that you get is the principal stress so far, right? Okay, so to be useful, okay, in the finite element software or analysis itself, okay, what we would want to further or see, okay, check on what is the one meter stress. Okay, so again, this is another type of typical stress that we always check for the result. Okay, VMS. Okay, so for the 1 meter stress, the formula is given as such. Okay, so you can Google it, okay, to refer to this, right? So this is the 1 meter stress, and the 1 meter stress, okay, basically is useful, okay, for to determine whether the material is yield or fracture for a ductile material. Okay, for a ductile material, right? Ductile material, for example, is metal. Okay, they can yield, they can change form. Okay, so it would be useful, okay, for this type of problem. Okay, so this is how you can get it, right? So the one meter stress is calculated in this form where you have the principal stress. Okay, these are the principal stresses. Okay, in the 1 should be x, 2 should be y, 3 should be z directions. Okay, this is referring to a three-dimensional cases. Okay, so you would expect that kind of average, so-called average stresses occurs on the material, right? So basically what they found out is that if we use the one meter stress calculations or criterions, okay, let's say you get a stress on your specimen, okay, in your analysis you get 300 megapascal, right? 1 meter stress is 300 megapascal, meaning to say there is a high chances, okay, that this 300, let's say 300, let's check. Okay, so 300 is somewhere here, all right? Okay, so 300 meaning to say if the stress is 300 megapascal, the highest one, meaning to say if we apply this mouse steel, it will not it still not reach the limit, okay, the elastic limit, meaning to say it still behave like the normal steel. Okay, it doesn't reach the yield or the ultimate or the fracture part yet, right? So if let's say this is 400, meaning to say you will identify that part will now start to deform and it will, or maybe it start to yield and it will not return to the original form. Okay, this is the usefulness of the one meter stress in the finite element analysis, to identify where is the locations that actually exceed this characteristics of the material itself, right? So whatever we get, okay, we still have to interpret, and this interpretation is based on the knowledge that we have, okay, based on the stress strain diagram of your maybe mouse steel, aluminium, or whatever it is, okay, to check, okay, whether the design part will actually yield or fracture or not. Okay, that would be the one meter stress usefulness of. Okay, then for another type of criterion, you may also found that in the finite element software, they can also calculate the Triscal yield criterion for you. Okay, Triscal stress, okay, Triscal yield criterion or Triscal stress. Okay, and this type of criterion would be useful to find out what is the maximum stress of the material before yielding, okay, before it start to yield. Okay, so this is another useful results. Okay, and usually these Triscal methods are lower as compared to the one meter method. Okay, so this is where different type of so-called criterion, one meter stress, principal stress. Okay, again, principal stress is used to calculate, okay, the different criterions, right? So that criterion will predict whether it will behave exceeding the limits of the material or not, right? So it depends on what type of approximations of the criterion that best suits for your problem, right? So this one, you may want to know what is the maximum stress occurs before it yield, okay, and so on, right? So the predictions between these two are actually very small. Okay, so you can either use one meter stress or Triscal yield criterion. It really up to you, to select, and also it's good that you can get some comparisons, like maybe papers, research papers that trying to compare the real experiments and which one they get closer, okay, that predicts closer, okay, whether we use principal stress or one meter stress or Triskal yield criterion that predict better, okay, for certain failure conditions, okay. So this is one of the examples of the one meter stress, okay, visualizations in the FEA model, right? So it shows the one meter stress and so on, okay. So for the brittle material, okay, we would mostly choose the maximum principal stress, okay. But for the ductile material, we usually select the one meter stress or the Triskal criterions to detect whether there is a fracture or there is yielding or not, okay. So it's very depending on the type of criterion that you use, okay, to evaluate the problem, okay. So let's say you have this problem, okay, and the maximum is 493, okay, 493 power 8, meaning to say this is 49 megapascal, right? So let's say this is 49 megapascal maximum, maybe occurs along this line, right? So 49, you have to check whether 49, where is 49? So maybe it's here, okay, 49. So it's well below the elastic limit, okay. Therefore, yeah, it may be safe to use in this case, right? So this is how we use, okay, all these criterion to be useful, right? So remember, whatever you calculate for the CST previously, you only come up to the point of the principal stress, okay, and that principal stress will be used to calculate one meter stress, or maybe you may use the principal stress as well, the maximum principal stress, to predict whether the brittle materials will fracture or not, right? So that is how you use, okay, all this knowledge for the studies of the problem, right? So yeah, okay, so this is another examples whether you should use principal stress, okay, how you should use principal stress to identify buckling as well as compressive stress, right? So different stress will give you different value, okay. So which value you should believe, okay, or use depends on what type of limits you would like to consider, okay. So that's all for these sessions, okay. So we will continue again next week on the next type of element, rectangular plane element, quadrilateral elements, okay, in the next lecture, right? So any questions so far? If no, we will end these sessions, and don't forget to try the two examples given, all right? Okay, so just try to solve it by hand, okay. Use your methods, just follow the examples and calculate, okay, accordingly, right? So any questions? So far no questions, right? So I hope this will help you to understand what values you should use, okay, and how they are related, okay, what are the principles behind it, okay, why you get those values, okay, and how you use it to interpret your analysis. Alright, so no questions so far, so we will end these sessions for today and see you again next week, right? So stay safe everyone, and bye bye.